Good to go. Anastasia is typing. We'll see if she has something exciting to say. So, recapping things there. I sent out an email earlier today. People see that? It's okay if you haven't, just because maybe you haven't checked it. But I did send out an email earlier today just doing updates. So muscle quizzes are in the process of being graded. Should be done by the end of the day. You've got a nervous system quiz that will be due tonight, lab quiz. And that's going to be on the neuron itself. So you'll see in the labeling exercises, the model of the neuron that we have, identifying different parts of the neuron. There'll be a sheep brain on there as well, photo of the sheep brain pointing to different areas. So, talking about different lobes of the cerebrum, or the thalamus, or the hypothalamus, and the pituitary gland that hangs off of the hypothalamus, different parts of the brainstem. You'll notice that the sheep brain, of course, is going to be oriented differently than our brain. The brainstem is going to come off horizontally, right? Because their spinal cord is also oriented horizontally. So it's not going to come down like ours is. But you're still going to see that anterior bulge, which is going to be the pons, and then the medulla oblongata is going to be down below that for our areas of the brainstem. So make sure, like usual, that you do the labeling exercises so that you can see those pictures, because we'll use those same exact pictures on the quiz. Also, there should be one of those where, like the muscle one that you completed recently, when it's pointing to brain areas, you'll have to know a function for each of those brain areas. Now, in the description and in the lab manual, it'll kind of give you those functions as well. But just make sure you've studied up for the brain areas listed in the instructions, in the lab instructions. You know those brain areas. I think it's like 10 or 12 of them or something like that, and a function for each, okay, just a short function. There's probably a couple other sections of the quiz as well, but I can't remember them right now. Maybe about the reflex arc or something like that. But it'll say that, right? In the section it says, for the quiz be able to. Okay? Okay. Then, in terms of our schedule, like you saw in the email, or some of you did, Wednesday is our next exam. Right here, like usual, we'll start with the exam, and then we'll do a little bit of lecture afterwards. The exam is going to cover all the way to endocrine system, which we should get into today, finish up tomorrow. Okay? So it's going to be muscular through endocrine. And this one's going to be mostly multiple guess. There will be a handful of short answer questions on it. Okay? So I think there's like 42 multiple choice questions, each worth 2 points like usual. So that's 84 points of multiple choice. That leaves only 16 points of the short answer questions. Okay? Okay. So where we were last time, we were looking at our special sense organs. We had gone from our different receptors, which were just kind of simple receptors, and we said that there's a lot of different receptors because each one responds to a different stimulus, right? So we talked about some of the simpler ones that are like naked wires, or maybe they have a little kind of head to them or something like that, but nothing like these different whole organs that are dedicated to a particular sense or stimulus. So some of the ones that we covered before were what? Some of the sensations or receptors. Pain, right? Nociceptors, right? That's the one that doesn't say receptor, it's just nociceptor, yeah. What else? Thermoreceptors, very good. For temperature, we found out that there was both ones for hot and ones for cold, and then there was at least one more. Oh, yeah, chemoreceptors will certainly, we mentioned those, and we will talk about those more because taste and smell are both chemoreception, binding of chemicals to a receptor that gets them to generate an action potential or send a signal into the brain. And then we were talking about touch receptors as well, mechanoreceptors. They were kind of telling us what's going on with the body. Are we leaning up against something? Is my muscle stretched or something like that? Okay? So those were pretty simple ones. Now we've moved on to the special sense organs. And we started out with the eye, and we said that the eye is going to be sensitive to light, right? So there's going to be photoreceptors somewhere in that organ. Now, we also talked about the fact that different animals have different types of eyes. Some of them will have eyes that only tell them whether it's light or whether it's dark. And so those are more like eye spots or something like that. It's just very, very simple. Some small invertebrates maybe have eye spots. They can tell where it's dark or something to hide or light, so they'll go to it or something like that. But our eyes, as well as eyes in many other organisms, are image-forming eyes. So not only will they tell us light and dark, they'll tell us color, they'll tell us shape, they'll tell us details about what we're seeing. Okay? So what we find is that there's a number of structures of our organ dedicated to gathering light that are going to help us to form an image and to control kind of what we're seeing at any given time. We're also going to find there are different types of photoreceptors that we have in our eye. So there are going to be lots of different cells that will sense light, but we'll find that some of them are for low light conditions, some of them are for bright conditions, some of them for color, etc. Okay? Okay, so we had done a little bit of kind of tracing pathways into the eye already. We talked about some of the surface structures. So the very first surface structure was the cornea, right? We said that that is going to bend the light rays, right? It's going to refract the light. It's going to take all that light that's out here. It's going to pull it in so it can go through the pupil, which is that hole in the center of the iris, okay? Then after the light goes through the pupil, it's going to go through the lens which is also going to bend those light rays again. We know we can change the shape of the lens because we've got these ciliary muscles attached to these suspensory ligaments that are going to be pulling on it or relaxing, and that will change the shape. And that is going to bring all the light rays together at the back of the eye. Now, the other thing that we were talking about is that at the back of the eye, we have the retina. And the retina is the innermost layer of the eye, and that's where the photoreceptors are located. We talked about two specialized spots on the retina. Where the pointer is right there is the fovea. We said that is the area of the retina where you have the best vision, the most detailed vision, okay? We'll find that in the fovea, we have only a certain type of photoreceptors. So we have two different categories of photoreceptors in the eye. Do you guys know those two different types based on their shape? Some people know from other classes. Cones, right? So there are cone photoreceptors, and then there are rod photoreceptors, right? And so the cones are for color vision. So you can think of the C's matching up there, color vision for cones, okay? The rods are for low light, or you could say night vision, kind of. And so the cones are much less sensitive, meaning that they need a lot of photons, a lot of light to hit them to make them go off. So they find in these conditions where you're seeing right now, and when we get to low light conditions, then the rods take over. It's too little light for the cones to actually for them to be active, but it's just fine for the rods because the rods are very, very sensitive. But the cones are going to give us color vision. When we say that the rods are going to operate kind of at night, you got to think about low enough light conditions where you can just barely see shapes and things like that. You can't even see any color. Once you start to perceive color, that means there's enough light coming into the eye that your cones are actually operating. Okay? So you're talking about like in your bedroom or in the house, like you're trying to sneak into your house after when you were supposed to be there, and you're leaving all the lights off, and you're like, oh, okay, there's the coffee table, I think, and I can see the couch there. That's when the rods are operating, okay? Like I said, you can actually see the color and patterns of the couch, or you can actually see, you know, some of the color and print of the magazine on the table or something like that. That means there's enough light in there that the cones are operating, okay? In any case, the fovea, that area where we have the best vision, the most detailed vision, is only filled with cones. So that little area right there has only cones in it, no rods. And that kind of makes sense because if you're going to see detail, you've got to have enough light illuminating the thing that you're looking at for you to see that detail, right? You're not going to see very good detail in really low light conditions. So the fovea only has cones in it. So it's kind of a specialized spot for seeing things. The other specialized spot that we talked about is the optic disc, which is just inferior to it, where we see the optic nerve hooking in. And we said the optic disc is almost the opposite, right? The fovea, we have really good clear vision, and the optic disc, we basically have no vision, right? So the next lab that you do is actually on special senses, and that one, you'll see models of the eye and models of the ear and stuff like that, and there'll be some exercises for you to do having to do with vision, right? So there's one that has to do with visual acuity. That's the one where you see all the different letters, and you're supposed to read them with one eye from 10 or 20 feet away, etc. And then there's also the one that's for color vision or color blindness to see if you have all of the different cone types that you're supposed to have. And then there's another one that tests the blind spot like we talked about on Thursday with the little circle and the X. Okay? So we said that there's no actual vision occurring there at the optic disc because all of these different axons for all of these different, coming from all these different cells of the retina are leaving the eye at the optic nerve there. So there's no actual space for there to be photoreceptors right there. But the brain does a really good job of filling that space in. All right, so we said that the innermost layer, seen here kind of in pink, is going to be the retina, where the photoreceptors are located. There's a black layer in the middle there that's called the choroid. And the choroid is the vascular layer. It has the blood vessels in it. You can imagine that with the millions of cells that we have inside of the retina that are receiving light all the time and changing into an electrochemical impulse, etc., there's a lot of activity there. They're going to need a lot of blood in order to perform their activities, right, for oxygen, glucose, and all that stuff. So the choroid layer is all of these blood vessels that are underlying the retina to make sure they're getting what they need in terms of those cells. So that's the middle layer. And then the outermost layer, the white of the eye, is called the sclera. And of course, we can see the sclera, the white of the eye here, but it goes all the way around as well. Okay, so that's all sclera right there. And that's the outer protective layer. It helps to give the shape of the eye, etc. Now, if you were to follow that layer around towards the front, you can actually see that here it's the sclera, but as it comes to the front, you can see that same layer gets clear instead of white and becomes the cornea, right? So the cornea and the sclera are the same layer if you were to trace them around, but where it's opaque and white, we call it the sclera, and when it's clear in the front, we call it the cornea. Okay? That's sometimes called the fibrous tunic. It's the outermost layer and it's the thickest layer. Okay? Okay. So those are all the outer structures of the eye as an organ that's supposed to help us see. Now, if we look at some of those structures in terms of their role, we already talked about the cornea that helps to bend those light rays to get them into the eye. We talked about the pupil, which is really just a hole in the middle of the iris, which is going to control the amount of light that goes into the eye. And in the iris, we've got two different types of muscle, like we were talking about before. We have circular muscle, like you see here. And when that is stimulated, it's going to constrict, and that's going to shrink down that pupil. And then we actually have radial muscles, a separate set of muscles, that when they're stimulated, that's going to pull that hole open. It's going to dilate the pupil, and it's going to allow you to see more. So technically, the radial muscles that you see there are under sympathetic control, and the constrictor muscles are under parasympathetic control, right? Because when you're really scared, those pupils are going to get really big, right? You're going to be in some sort of stressful emergency situation. So the iris helps to control the size of the pupil, which helps to control the amount of light that's going in the eye. We said that the cornea and the lens both bend light rays. The cornea could bring it into the eye, and the lens in order to form a clear image on the back of the retina. And while we can't change the shape of the cornea, unless you're like putting your finger on it or something like that, we can and do actively change the shape of the lens. And so by changing the shape of the lens, if you look to the right of that image there where the lens is, by changing the shape of the lens and making it skinnier or fatter, it changes that focal point. Okay? So it depends on whether we are trying to focus something up close or far away, but we want to make sure that we have a nice clear image back on the retina there. And so that change in shape that the lens undergoes is called accommodation. So it's not like accommodation like Motel 6 or something like that. It's a physiological term that refers to the shape change that goes on with the lens in order for us to focus the particular image on the retina. Okay? So the lens of the eye, its function is also to refract or bend the light rays. And then finally, we're going to get this light back to the retina. Okay? Now notice there are a few chambers of the eye as well. Let's get back to this other image. You can see that there is a chamber up front here, a smaller chamber up front here between the cornea and the iris. And then there's also a chamber back here, a bigger chamber. Okay? So the first one's called the anterior cavity, right, in the front. The big one is called the posterior cavity. And in each one of those, there's a fluid or a gel. Now, in the anterior cavity, there is a fluid that's called the aqueous humor. You can see it listed underneath where it says cornea. And that fluid is always going to be kind of circulated through there. And then in the back, there's what's called vitreous humor in the posterior cavity. And that's more of a gel-like consistency instead. And so those help to give form to the eye, etc. They help to give it a nice round shape. And when you hear about things like glaucoma, that's where the fluid, like especially in the anterior cavity of the eye, it's supposed to be circulating. We take some out, we put some new stuff back in, and it helps to maintain the shape of the eye. But when there's a drainage problem or something like that, or an overproduction of that fluid, then the pressure in the eye goes up, right? We're jamming all this fluid in there, it's not being able to drain, so the pressure in the eye goes up. That's what glaucoma is. And so when people have that, they have to take drops, et cetera, to try to help regulate that pressure so the pressure in the eye doesn't get too high. Because if the pressure in the eye gets too high, it compresses the blood vessels and things like that, and it puts pressure on the delicate retina on the inside, and so their vision can be impaired. And of course, that's one of your major excuses for getting your medical marijuana as well. So, there's pros and cons to it. All right, so because the light rays, again, they're going to go through the anterior cavity, they're going to go through the lens, they're going to go through the posterior cavity, and end up back there at the retina. Okay? So this image here, which is taken from a different book, shows us the retina. Here's the retina from here to here. Okay? Then there's the choroid layer with all the blood vessels, like we see in there. Getting a little wild there. And then there is the sclera that's out here, the white of the eye. Now, when we look at that zoomed-up retina, we can see that there's lots of different cells there. They're showing you in different colors so they can show different types of cells. But back here is where we see our photoreceptors. And you can see, here's a rod. Okay? This is the whole cell of the rod right here. And then here's a cone. And you can see that there's three different types of cones. You see there's green cones, and red cones, and blue cones. Okay? So there's only one type of rod, and they're all shown in gray, and there's three different types of cones, and there's millions of these cells all around the retina. Now these other cells that we see right here are cells that will relay the signal and amplify it and kind of change it in slight ways before it goes out of the eye via the optic nerve. So the light rays come in, they're going to come from the left side of your screen, they're going to go through the different cavities of the eye, they're going to go through these outer layers of cells in the retina, and then they're going to get to the rods and cones. The rods and cones are going to be stimulated by that light. They're going to do that translation, okay, or what they call transduction. It's going to change it from a light stimulus into an electrochemical impulse, something that the brain can understand, okay? So once it does that, and we'll talk about how it does that coming up, once it does that with those photoreceptor cells, then it's going to relay that signal to some of those other cells in the retina. It's going to relay it to the bipolar cells you see in bulbs in the middle, the bluish ones. Those are going to relay the signal to the ganglion cells that you see there, those yellow ones. And then notice the axons of those ganglion cells right there are going to all come together and they're all going to exit out the optic nerve. And that's why we have that big bundle, like almost like a telephone cable with all those wires in it. All those axons there from all the ganglion cells are going to exit the eye. Okay? Now, one other thing I want to highlight before we talk about those photoreceptor cells in more detail, notice that those bipolar cells, those blue ones in the middle, just as bipolar cells, technically those are bipolar neurons, right? So we said, when we introduced the neurons last week, we said there are three functional groups and three structural groups of neurons, right? The structural groups are multipolar neuron, which is the one we're looking at for the most, right? We saw the dendrites, and then we saw the one axon coming off of it, right? That's the multipolar neuron. That is our best example of a bipolar neuron, those blue bipolar cells. You can see that there's a soma or cell body in the middle, and then there's only two poles sticking off of it. One's the dendrite, and one's an axon, okay? So the third class of structural neuron is going to be a unipolar neuron, where you just have that one soma or cell body, and you have that one little extension coming out of it, and then it splits off through there. Okay? So that's an example of one of our 3 types of structural neurons. Functional neuron types, just as a reminder, we have sensory ones, relaying information into the brain and spinal cord. We have the interneurons, which are the little ones that are making the decision in the central nervous system. And then we have a motor neuron, which is relaying the information out to the effector, like the muscle. Okay? Okay. So let us take a look more at these photoreceptors. So again, here we see 2 different types of photoreceptors. There is a cone cell, and you can see that their outer segment right here is shaped a little bit pointed, something they thought was like a cone. Here's a rod, and we see that their outer segment is shaped a little bit rod-like. But this whole thing that you see right here is the cell. So you can see it's a very unique cell shape, right? Very different than the round, generic structure that we were seeing before. So all of this is a cell. You can see the soma, the cell body, the nucleus right here and right there. And then you can see we have this big specialized outer segment there. So it's in that outer segment where it's shaped like a rod or a cone where we have what are called photopigments, the actual molecules that will catch the photon of light and change that signal into an electrochemical wave. Okay? So over on the right-hand side, what they're showing you is an example of a photopigment. This is what's called rhodopsin. This whole thing that we see right here is called rhodopsin. You can see there's 2 parts to it. The blue kind of dumbbell part of it is called opsin. That's kind of the protein housing. Okay? Then there's this little molecule in here that's called retinine. And it's zoomed up down here and down here. That's the retinine molecule. Now notice, in the dark, okay, that's why it's all black right there, in the dark, with this rhodopsin molecule, that little retinine molecule has a kink to it. See how it's bent, like right there? And then when it actually absorbs light, notice that little kink that was right here straightens out. Okay? The actual molecule will change shape when a photon of light hits it. In essence, the photon of light is going to be energy, so it's enough energy to unkink that molecule. And when that happens, what happens is, now it doesn't fit so well in that opsin molecule. And so then after that, there's this whole domino effect, this whole series of chemical events that lead to that cell releasing neurotransmitter to communicate to the bipolar cell releasing neurotransmitter to communicate to the ganglion cell, and then the ganglion cell sends that big action potential in the optic nerve back to the occipital lobe, and then your brain goes, hey, I saw something over there. Okay? So it's that rhodopsin molecule, that photopigment, which is the specialized part of these photoreceptors that allows them to change that light signal into a neural signal instead. Okay? So like we said, photopigment is made up of the bigger opsin protein, and then that little retinine molecule that has either a bend to it in the dark or straightened out in the light. Okay? And that retinine comes from vitamin A, right? So vitamin A is also known as carotene. Retinine is a molecule that is chemically changed just a little bit from the original carotene, from the original vitamin A, and that's where we will kind of recycle and reproduce that retinine molecule in all of your different photopigments and all of your different photoreceptors. So when your mom and dad were talking about, that you should eat your carrots because it's good for your eyes and stuff like that, they weren't kidding. That's the whole idea there, is that those little molecules, those retinine molecules, as they're bending and straightening out and stuff like that, and we have to swap them out and put a new one in, all of that, after time, wears out these molecules, so we need to replenish them. And any fruit or vegetable, more so the vegetables that are orange or red or something like that, it's the carotene molecule that gives them that color. So the darker they are in terms of red, like a red bell pepper as opposed to an orange as opposed to a yellow one, the darker they are, the more of that carotene is in that vegetable, and the more you're getting as you're eating it. There are people, like more in third world countries and stuff like that get what they call night blindness because they don't get enough of that carotene in their diet, and so their photoreceptors don't have enough of that retinine in them, and they don't do well seeing at night because their rods don't have enough photopigment in them to let them see appropriately. For you guys, and for most of us, right, it's not an issue. But you should still eat your vegetables anyway. Okay. So, all of our different photoreceptors have this type of photopigment inside of them that allows them to be stimulated by light. Now, we said that with the rods, okay, there's only one type of rod. There are three types of cones. There are blue cones, green cones, and red cones. Now, they're not equally divided. The cones aren't equally divided between those three. You actually have the most of the red cones, and then of all your cones, you have about a third that are green, and a relatively small population that are blue. But it's the combined stimulus of these three different types of cones that allow you to see color, okay? And we're going to talk about that in just a couple slides. Now remember, though, that it was there in that fovea where we actually have a very high concentration of those cones that allow us to see good detail, okay? Now this figure right here, your book has a similar one. This is from a different paper, but what it shows you here is it's showing you for our different photoreceptors where those photopigments are going to absorb light. What wavelengths of light they're going to be most sensitive to. Okay? So, on the x-axis of that graph right there, you can see it goes from 400 to 700 nanometers. That's our range of what humans call visible light. Now, we said that things like lizards and fish and bugs and stuff like that can actually see beyond that. But for us, that's visible light. So it's violet over towards the shorter wavelengths. It's red at the opposite end in the longer wavelengths. Okay? So look at the rod one that you see in the middle there. So the rod one says 498 nanometers. Okay? So that means that rods are best stimulated by a light of a wavelength that is approximately kind of a blue-green kind of color, about 500 nanometers. Okay? So that means for a rod, if you give it a color of light that is approximately that blue-green color, about 500 nanometers, then basically almost all the different rods will go, hey, I saw something. Okay? Now notice it's a curve, though, right? It's like a hill. That's almost like what we would call like a frequency curve, or basically like a probability curve. If you give a rod a light of about 500 nanometers, almost all of them are going to go off and go, hey, I saw something. Now, if you go on the other sides of those curves, like say you go up to 550, if you look at where 550 is and you go up, you can still see it'll hit on that line of the rod curve, okay? But it's down, say, at like 30 or something like that, like 30% or something. So that means that if you shine a light that's pure green like that, about 550 nanometers, only about a third of the rods will go, hey, I saw something. It's not the best stimulation for those rods. But you can see it spreads over a lot of the visible spectrum that we see there, okay? But all the rods have that same pigment. It's optimally stimulated about 500 nanometers. It gets worse and worse as you spread it out from there. Okay. Now, color vision. So with color vision, in order for us to see colors, you have to have at least two different photoreceptor types. Because what the brain is going to get is it's going to, in essence, get information from your different color receptor types and then compare that information in order to decide what color you see. Okay? And the analogy that I typically use with that is that if there's a car accident or something like that, and then the police show up and they want to find out what happened, they don't just ask the one driver, right? If they ask the one driver, they're going to get one opinion, one view of what happened, and they're probably not going to understand the entire picture, right? So in order to get a good idea about what actually happened, they ask the two people driving the separate cars, they ask people riding, they ask anybody else who witnessed it from the street, and then they have a good idea about what actually occurred. It's very accurate that way. Same thing in terms of color vision. In order to figure out what color we're actually seeing, we need at least two different photoreceptors to say, hey, I saw this, and say, hey, I saw this, and then the brain compares the information that it got. Okay? So if you have two color photoreceptors, then you can discriminate color, right? If you have three color photoreceptors, you can also discriminate color, but now you can do it better, right? Just like at the accident, if you have three witnesses, you've got a better idea about what happened compared to two. Four is better than three, et cetera, et cetera. Okay? So, blue cone, green cone, and red cones. We have three different color photoreceptor types. And when a light stimulus comes in, each one of those three different types are going to get stimulated differently depending on the color of the light coming in. And they're going to send their signal into the brain, and then the brain is going to sort it out and say, oh, okay, I get it. We saw orange based on what it got from those three different types. So let me show you a similar picture like this. Again, taken from a different book, similar to the one that you have in your book. But it's the same type of curve here, right? You see 400 to 700 nanometers on the x-axis, and we see light absorption, percentage of maximum here on the y-axis, okay? So blue cone, green cone, and red cone. So we're going to use three different examples. We're going to first use an example of shining a blue light into your eye, and what are these three different color photoreceptors going to do, okay? So if we shine a blue light in the eye, say about 425 nanometers, like you can see here, I should do this, right? Like you can see here, blue, okay? Look where it hits on these three curves, right? On the blue cone curve, it almost hits right at the top of the best light color to stimulate the blue cones, right? That's why they're called blue cones. So basically, 100% of those blue cones are going to go, hey, I saw something, and the blue light goes in the eye. But notice that same color of light, it doesn't overlap at all with the green absorption curve or the red absorption curve, okay? So that means the green cones, even though it's a blue light going in there, green cones aren't going to get stimulated at all. They're going to stay silent. They didn't see anything. Red cones, same thing. It doesn't overlap with what they would normally be stimulated by, so they're all going to be quiet. So what the brain gets is red cones, quiet. Green cone, quiet. Blue cone, way, 100% of them said they saw something. So the brain says, oh, okay, I saw blue. Okay? Sounds pretty simple, right? Don't have to worry about that. Blue cone's all stimulated. I saw blue. All right. Let's look at the next one. So, green. So a green light goes into the eye. A green light is about 475 nanometers, something like that. Now let's look and see where it hits on those absorption curves for different photoreceptors, right? So you can see it hits about here on the red curve, about there on the blue curve, and higher up, even better, on the green curve. So what does the brain get? About 2/3 of the green cones go, hey, I saw something. About a third of the red sends the signal in, and about a third of the blue. And so the brain takes that information and goes, oh, I get it. That means we saw green. Okay? There's no real way to describe a color, right? So you can say, how would you describe red? You're like, I don't know, right? We just agree that color on his sleeves over there are red. We just kind of agree on it, right? So I say it's red, and you guys all say it's red. But how am I going to describe that? Well, it's not blue. It's like fire color. And we all know that fire color is kind of red, so then okay, then that's red. You know what I mean? So this is, by wavelength, you can actually say that red is, like 650 nanometers. But in any case, for what the brain gets, in order for it to decide that you've seen green, most of the green cones are going to go off, a little bit of the blue and a little bit of the red. Okay? All right. Now let's take this last example, which may be the toughest one often, right? Because on a certain level, people go, oh, I get it. I understand how we can see blue. I understand how we can see green. I understand how we can see red. But how do we see stuff like orange or yellow, right? Because we don't have a yellow cone. How does that work? So again, it's all depending on what the brain gets. So here's the yellow light coming in, right? Yellow light's about 550 nanometers. Let's follow it up. Well, you can see it doesn't overlap at all with the blue curve, right? So the blue cells, blue cones are going to be silent. If we follow this up, notice it hits the green curve and the red curve, absorption curve pretty high there. So most of the red cones and most of the green cones go, hey, we saw something. Blue cones are silent. So the brain takes that information and translates that into, okay, that's what we call yellow. Most of the red and the green cones saying they got excited, no blue cones, that's yellow. Okay? It's not mixing paint. It's not like, like we said, green, red, gank it brown, or anything like that. It's what photoreceptors are actively sending signals into the brain, and the brain decides that's what we call yellow. Okay? Now everybody's set of cone photoreceptors are slightly different. They think there's actually some perception differences between how women see color and how men see color. And it may have to do with how they select clothing and fashion and things like that. Who knows? It's possible. But when we say something's red, the color that I see in terms of red, right, it's probably slightly different than what you see in terms of that particular shade of red. But it's similar enough that we can all go, yeah, okay, that's red. If you're into interior design or something like that, then you start using all these other synonyms for red colors, maroon, and all these other things, and then you might start to find some differences. But for the most part, we all have these three different color photoreceptor types, these three different cone types, and it's a combined stimulation from those three that allows us to see the millions of colors that we can discriminate. Okay? So again, if you have two color photoreceptor types, you can still see color, but just not as well, because your brain's only going to get information from two different sources. So there's more chances that it's going to be a little bit unclear about exactly what that color is. Okay? So, for instance, people who are colorblind. People who are colorblind tend to have two color photoreceptors, and they're lacking one of the three, right? They're usually lacking like the green or the red. So they can still see some colors, but as they get out towards the longer wavelengths, like oranges and reds and stuff like that, they have a hard time discriminating those from like things like greens, etc. Now usually, does anybody know anybody who's colorblind? So usually, is it a guy? Is it a woman? Okay. Usually, so that's very interesting. So, color blindness is a genetic trait, okay? It's a malfunction in a gene, one of those little recipes that we have in the DNA. And it is attached, or it is found on the X chromosome, okay? So it's called a sex-linked gene. It's attached to the sex chromosome as opposed to like chromosome 2 or like 18 or something like that, okay? So, it's a problem with that gene on the X chromosome. Now, for a woman, you've got two X chromosomes. So if you've got one with a defective color cone gene and one that has a fine one, then basically the fine one will cover up the fact that you have a defective one, and your vision will be okay. You'll have all three different color photoreceptor types. Because even though it may consider this one, it's like, oh, okay, that one says this is how you make the cone photoreceptor. But for a guy, right, a guy in every one of his cells, he has one X chromosome and one Y chromosome. And if the X chromosome is messed up somewhere, there's usually not a complementary Y part of the Y chromosome to help cover it up. Okay? So, what happens is most people that are colorblind are men. Because what will happen is they'll get that defective gene from their X chromosome. Where does the X chromosome come from? Their mom, right? So they inherit that defective gene from their mom. They get a normal Y chromosome from their dad, but they have no way to offset that defective one that they got from their mom. So they are in fact colorblind. They'll have two different color photoreceptors. They can still see color, but not all the different colors that you and I can see. Okay? Now, if you have somebody, the female who's colorblind, what that means is they have one X chromosome from their mom, they have one X chromosome from their dad, and both of those were defective. Okay? That means the mom was like a carrier of that X chromosome, and the dad was had the trait as well. The dad was colorblind, and so then the child has two defective genes on both X chromosomes, and so then that's a woman who's colorblind. That doesn't happen very often, because both parents have to carry that recessive gene like that. So it's interesting. I don't know what the statistics on it are, but men are much more common to be colorblind like that. Okay, and then the man, in terms of the inheritance, right, the man can only pass on that defective X chromosome to his daughters, because of course to all of his sons, he's going to be given Y chromosome instead. And then the son can only inherit that colorblindness gene from his mother. It always goes that way, because it's always on the X chromosome. Okay. So anyway, people who are colorblind, they're not colorblind, they can see some colors, they just can't see as well as you and I. The other thing that I would tell you about color blindness is that dogs are not colorblind. Okay? It's a common misperception that people think that dogs are colorblind. But dogs just happen to only have 2 of the tone types instead of 3. So they're like a colorblind human. They can see some colors, they just can't see all of them. And so when you give them a particular ball or something like that, for the most part they care about the ball, whether it makes a noise or something like that. They don't care about the color, right? But they've actually done tests. There's some tests a long time ago, like in the 80s, where they did scientific experiments where they trained the dogs with a particular food type and they put them in a particular colored item. And so they trained them, they would always get treated in this particular green ball or something like that, right? And then after a while they get trained up, oh, the green one, that's where the food is, right? And then what they would do is they would take new balls, green one, and maybe a red one, and a yellow one, and they would put them out there and see which one the dog would go for. And if they could tell color, right? This is a clean ball. It doesn't smell like food or anything like that. If they can tell color, they're going to go for the green one because that's where they learn where the food was found. And if they can't, then they're just going to randomly choose any of them. Right? So they've done those experiments, and they can tell color, just not as well as you and I. Okay. So 3 is better, 4 is better still. Like we said, there are animals like butterflies and stuff like that that have 4. Here is the king of the color vision world. So this is the absorption spectra for Anatomy, which is a marine crustacean. It's also known as a mantis shrimp. So that's actually what I studied for my PhD. Is we were looking at vision in mantis shrimp and kind of vision in marine organisms. And so we have 3 different color photoreceptors between 400 and 700 nanometers. As you can see, they have 8. They have an additional 4. Some species have an additional 4 between 300 and 400 nanometers in the UV. So they can have more in UV than we have over the entire spectrum. So not always are we considered to be the top of everything in terms of our body conditions and stuff like that. I'll show you some pictures, maybe a break, I'll show you some pictures of mantis shrimp, what they look like. Okay. So now we have a decent understanding about how the eye does its job in translating a light signal into an electrochemical impulse. Okay? Once that has occurred in the retina, we're going to round out those optic nerves. You see the optic nerves going back. They go to the thalamus, right, the core of the brain, the relay station, and that routes it back to the occipital lobe in the back of the cerebrum for processing. So we have to sort out all the information that we're seeing. Colors and shapes and edges and motion, etc. Okay, all that has to be separated in order to figure it out. There's a lot of information. Notice that there's some of that crossing over that we talked about before, from one side of the body to the other side of the brain, but it's not exactly the same. Notice that, for instance, the left side of each eye, left side of the retina in each eye, routes over to the same side of the brain. So you see how it goes over to the left occipital lobe. The right side of each retina, each eye, routes over to the right side, over to the right occipital lobe. And what that does is it allows the 2 eyes to compare the same information. So that part of the retina, for instance, my right side of the retina is getting light from over here. And so if we take that information from both eyes and send it to the same area of the brain, we can compare what we're seeing, right, like witnesses again. It also, having our eyes and visual fields overlapping there, it gives us what's called depth perception. Right? It makes it easier to target things and grab things specifically because your eyes, as they're viewing something, they're slightly off in terms of their angle, right? One's viewing it from the right side, one's viewing it from the left side. So if you have something out here, this one's viewing a little bit like that, a little bit like that, so you get that depth perception where you can see, this thing is right here, this far away from me, because that's a slightly different viewing angle. You can also do that, I mean, with one eye, right? You can estimate how far things are based on the size. As they get smaller, as they go farther away, but it's not as easy to do. Don't try it while you're driving, but you can try maybe walking or something like that. You can still tell depth, but you get the feeling that's not exactly the same. You don't have that comparison between both of your eyes. Okay. So that is vision. Fairly complex. Organ dedicated to it. Any questions about eyes and things like that? Let us do a brief anatomical introduction to the ear, and then we'll go to break. Okay? Okay. So the ear. The ear is also an organ that is entirely dedicated to some senses. Now, notice I said some senses and not just hearing. What we get out of the ear are actually two different sensations, technically three. Okay? You get hearing from the ear, but you also get balance or equilibrium from the ear. Okay? They're different structures, but they both come from some part of the ear. Okay? And when I say there's three, there's two different types of equilibrium. One's called dynamic or rotational equilibrium or angular equilibrium, and one is linear. Like if I close my eyes and I'm in an elevator, I can tell when we're moving down or when we're moving up without my eyes seeing things moving past them. Okay? So we have both hearing and equilibrium coming from the ear. So we're going to see that there's a number of different structures in there. So let's get the layout of the ear first. The layout of the ear shows us that there are three different sections to the ear. There's an external ear, there's a middle ear, and then there's an inner ear. Okay? So the external ear is going to be from here, from the eardrum or the tympanic membrane out. Okay? So that's going to be the external ear. Then the middle ear is going to be from the tympanic membrane until we get to the cochlea, etc. So between the yellow line and the green ear, the green line is going to be the middle ear. And in the middle ear, we have the ossicles of the three ear bones. Okay? We also see a connection here called the auditory tube or the eustachian tube that connects the throat to the middle ear. We'll talk about why. And then, lastly, we have the inner ear. And the inner ear is going to be from the green line to the red line, and that's where we're going to have all of our different receptors, the things that are actually going to translate some type of stimulus into an electrochemical impulse. Okay? Okay, so we have external ear, which is all this stuff out here. So you see this outer thing here? This is the auricle, or it's also called the pinna, right? This is basically like a big funnel. And it's trying to bring in all these sound waves from all these different angles and bring them in here into what's called the external auditory or external acoustic meatus. Okay? So in a way, that outer ear, that pinna, is a little bit like the cornea. It's trying to bring in all of these stimuli from all these different angles and bring it into one hole in the center. Okay? So we have the external auditory or acoustic meatus, which is going to bring these sound waves into here. Okay? Now, at that point, it reaches our tympanic membrane, also known as the eardrum. And that has, right, pretty straightforward common name there, because as those sound waves come in, it's going to cause that eardrum to vibrate, right, like beating on a drum. And as that eardrum or tympanic membrane vibrates, it's going to cause these three ear bones, the malleus, the incus, and the stapes to vibrate. So those are located here. And what they're going to do is they are going to beat out the rhythm from the tympanic membrane, and they're going to send it into the receptors in the inner ear. So again, here we see the external ear, that's where the sound waves are coming in. Here's our tympanic membrane, or eardrum. Here are three ear bones. The malleus is the first one, the incus is the second one, and then the stapes is the third one. Now these are ones that you used to call, right, the hammer, and the anvil, and the stirrup. Right? So those names come from the shape that they are. So somebody thought the first one kind of looked like a hammer, malleus, like mallet. Okay, malleus is the anatomical name. The incus, anvil is if you're in like a blacksmith shop or something like that, and they have that kind of T-shaped thing. If you watch cartoons, it's always dropping on Wile E. Coyote's head or something like that, right? A big T-shaped iron thing like that. That's an anvil. So a blacksmith would like take horseshoes or whatever and like hammer things out on it. Okay? So they thought that when they saw that bone, they thought that it looked like an anvil, right? But the anatomical name is incus. And then the last part is kind of horseshoe shaped, if you will, but more correctly, theory, like the stirrups of the saddle, right, where you put your foot, right, comes down like that, and there's a flat part. So that's the last part. Those are the three smallest bones of the body right there. We said we have 206 bones. Those are three in the left ear, 3 in the right ear. That's 6 out of the 206. The stapes, the last one, the stirrup, is the smallest bone, as we talked about before. So those bones are going to start bouncing around, right? So as the tympanic membrane vibrates, those bones are going to repeat that message and even amplify it. They're going to make it a little bit more forceful as it comes in to this inner ear. Okay? So that stapes right there is going to beat out that message on the little membranes called the round windows right about there. And then those vibrations are going to go, and they're going to move throughout this snail-shaped structure, which is called the cochlea. So that snail-shaped structure, the cochlea, is where our receptors are going to be located for hearing. They're going to be able to pick up those sound waves and translate it into something the brain can understand. Okay? And the only other thing that I would mention before we go to break is we said that this middle ear right here also has that little connection, which is called the eustachian tube or the pharyngotympanic tube or whatever. Okay? That's important because this connection here down to the pharynx, technically the pharynx is down here, like that. But that connection allows you to equalize the pressure in your ears. So when you're on a plane and you're going up, and your ears are needing to pop and stuff like that, what's happening there is the tympanic membrane has space, air on either side of it, okay? And as you're going up in the airplane, right, you're going up in the atmosphere, if you will, and there's less atmosphere on top of you. There's less pressure up there. And so what's happening is the pressure out here is lessening, and the pressure in the middle ear is still the same. And so the eardrum itself starts to curve out like that because the pressure on this side is less, and so it starts to move that way. And so then what you do, right, is you either chew gum or you pinch your nose and kind of blow. What that does is it forces air from the back of your throat up that eustachian tube to the middle ear, and that equalizes the pressure on either side of that membrane, and now it's the same. So as you continue to go up, you got to continue blowing, or if you're driving up into the mountains or something like that, you continue blowing air in there, and that equalizes the pressure on either side. Same thing if you're going down. Does anybody scuba dive? Marine biologist, so it's kind of necessary. So when you scuba dive, same thing happens, right? So when you're at the surface, you're at 1 atmosphere. There's 1 atmosphere sitting on top of you, right? When you go down, for every 33 feet you go down, there's an additional atmosphere of pressure on top of you. The water is more dense than air, right? So you could have 33 feet, now you're at 2 atmospheres. Go down to 66 feet, now you're at 3 atmospheres, etc. So all the time scuba divers are going down, they're also pinching their nose with their mask, and blowing in order to equalize the pressure. So what's happening there is the pressure out here where the water is now forcing and pushing in. So you need to equalize on either side. So you're taking some air up there and bouncing on either side. If you don't do that, then all of a sudden those tympanic membranes are getting pushed and pushed and pushed, and it's possible for you to actually blow them out because there's too much pressure just pushing on it instead. Okay. So we've looked at outer ear. We've talked about middle ear with the ear ossicles and the eustachian tube and stuff like that. What we're going to talk about when we get back from break is the cochlea and the inner ear, where we're going to sense hearing, and then we're also going to talk about equilibrium, where that comes into play in that inner ear as well. Okay? So let us take our break as we normally do. So about 15 minutes or so. You guys all right? We come back in a quarter or two?